Welcome to Unit 10, Day 3. Today we're going to be talking about sigma notation, which is just a funny way of writing to add up all of the terms of a sequence. So let's take a look. So this is the symbol for sigma notation, where this is an indicator of a starting term number. So this says start at term 1 and end at term anything you want. Now both of these numbers can vary. They don't need to be 1, and it can be as many terms as you want. It could be from term 1 to term 1,000 or term 1 to term 5. You can even start in the middle at term 8 and go up to term 10. This symbol is the capital Greek letter sigma, and it means to add. And over here would be a formula of some sort. Now, depending on the program used, this might also represent the same exact thing. So again, this would be the starting value, the ending value, and a formula. And all we would do would be adding up the values. Now, the formula is technically an explicit formula, so it wouldn't be a recursive formula. So like if I had the sequence 1, 2, 3, this is the recursive formula. A1 equals 1, and the rule would be an equals an minus 1 plus 1. This would be the recursive rule, whereas the explicit rule would just be an equals the first term plus the common difference times n minus 1, because that would be an arithmetic sequence. So this would be the part that would appear here. So the explicit rule would be what appears in place of n in this case. All right, so this is a written version of all of this in case that's not clear. So the variable in the problem, usually the term number. This is the starting term number, the ending term number, and this is the expression used to generate the sequence. So here's an example problem. It says find the sum of all of the first to fifth terms of this explicit sequence. So as an explicit sequence, it would be am, which, because the term number is m here, goes from 1 to 5, but the rule is for this sequence, multiply 4 times the term number squared plus 4. So this is the rule, and we're asked to sum those up. So for the numbers 1 through 4, we would just have to calculate the value for that. So if I take a 1 and plug it into the formula, 1 squared is 1 times 4 is going to be 4, plus 4 would be 8, which is where this comes from. Let's do that again. So we'll plug in 2. So 4 times 2 squared. 2 squared is 4. 4 times 4 is 16, plus 4 is 20. So we'll get 20. If we plug in 3, we will actually continue to go and we'll get 8, 20, 40, 68, and 104. So the sum of those values, which is what we're told to do, being given that we're given the sigma, the capital Greek S, is to add up all these numbers. So we just add them all up and we get 280. I did this with a calculator earlier when I wrote the answer key, so it's a bunch of big numbers and they could be really random in what they look like, so it takes a little bit of work. So what I recommend you do for each example is write down a table. So this one goes from 1 to 5, and we'll call this k because that's the term number, and we'll call this ak, meaning the value of the kth term. Then just add them all up and get a total, and that would be how to perform a summation. Now there is a summation feature in a calculator. I'll briefly show it, but I'm not expecting you to do that. I expect you to show work and show all the terms. But if we were to pull open a calculator, it's in math. For this one, it's this expression. So if you have a different calculator, it might work differently. But this can be done without a calculator if your ending value is not that large. If it's much larger, you would use a calculator for it. All right, so I'm going to leave the rest of these problems for you to try. Now we're going to see how to write, given the sequence. So if I gave you a sequence, how could I write this into sigma notation? So we're going to take a look at a few examples. Firstly, we're going to take a look at an example of an arithmetic sequence. So firstly, if we look at this first expression here, we have several terms. We have the term A0 all the way up to, this would be term 1, term 2, term 3, term 4, and term 5. So we would write this is the sum of n equals 0 up to 5. Now for a arithmetic sequence, that means the rule is we're adding the same number from term to term. Let's take a look at the terms. This goes up by 3. This goes up by 3. So this is an arithmetic sequence with a common difference of 3. A second way to find the common difference is to take any pair of terms. So let's say I took 11 and 14 and subtract the newer one from the older one. So if I did 14 minus 11, I would get d equals 3. So that's another way to find the common difference. So the common difference will go into the formula first. So it's 3 n. So the common difference goes in front of our variable, meaning it's going to be additional 3's will be added as the term number increases. So at term 0, we're going to have 0 copies of that term. Let me just use a different color for this so there's no confusion. So this is the common difference. And then we are going to, if we were to plug in a 0 here right now, we get 0, but our first term is 5. So we need a, kind of like a y-intercept. It's our 0th term. We write a 5 here. So that would be one way to write this. But this is specifically for writing a arithmetic sequence where we start at 0. If we were to start at a different term number, we would have to change the formula in some way. But this is always going to be A0. So for instance, let's say instead of labeling these numbers from A0 to A5, I labeled this from A1 to A6 instead. So it's just me labeling this differently. Then the problem is going to change a little bit. I'm going to write the sum of the terms from term number 1 to term number 6. I'm still going to write 3 as my common difference, but I still need to write whatever the 0th term would be for this expression. So based on this labeling, A0 would actually be the term that comes before 5. So if I were to go back to A0, that would mean to take away 3 units, I would get A0 would be 2. So I would write plus 2. And the reason for that is when I plug in a 1 here into this problem, it's going to give me 3 plus 2 is 5. So there are 2 ways to write it. I would recommend starting with term 0. So that would probably be a little easier. All right, let's take a look at a geometric sequence. So in a geometric sequence, that means we have a common ratio, so we're multiplying by the same value over and over again. And this one should be pretty clear that it's not an arithmetic sequence, because if we were to add, we would do plus 3, but 9 plus 3 is not 13.5. So clearly this is not a arithmetic sequence. To be a geometric sequence, we need to see what did we multiply by to get from 6 to 9. So that's 1.5. The shortcut for that is to pick any pair of terms and divide them, the newer one from the older one. So we'll say r in this case is equal to 9 divided by 3, which is 3. So 3 is our common ratio. Maybe I should have done that in red. So r is going to equal 3. So our first term is going to be A0, and our last term here, this would be A1, A2, A3. So in this case, we would say the sum of these terms from term 0 up to term 3 would be to start at 6 and to multiply by our common ratio. In this case, that would be 3. So this in this case is term 0, A0, times 3, which is our ratio to the nth power. In other words, for the term 0, you multiply by 3 0 times. if you were to label this from term 1, and that would make this term 4, it would change the formula slightly. So this would be the acceptable formula for starting at term 0. But if you wanted to start at term 1, the formula would be start at term 1, end at term 4. The rule is still start at 6, but multiply by 3. But I need to multiply 0 times for the first one. So I have to write, instead of n, I would write n minus 1. So the starting number has to get subtracted, so it becomes multiply it by 0 times. So I would recommend not starting with term 1 in either case, but you can. If you start at term 0, it's a little easier. You have a kind of a y-intercept to use in the formula. You also have a no subtractions to do to the exponent. Now, I included a special example, like just an other visible pattern, where it's not necessarily arithmetic or geometric, but it's not that complicated to figure out a rule. For this one, we'll say that our first term is a0, so the next one is term 1, 2, 3, 4, 5, a6. So the rule here is going to be find the sum from term 0 to term 6, and the rule is start at 1 over 3, and the rule seems to be, for the numerator, add 1. So I'm going to add n, because as the index increases, I'm going to be adding 1. And for the denominator, it's counting by 2's, so I'm going to say add 2n. In other words, as the index increases, add 2. So this is just for a special case. It's not going to be in the homework on Delta Math at all. I just wanted to show you an interesting problem. I included one of them in the examples below. So that would be over here. For the other examples, you'll have to look at them and determine if they are either a geometric or an arithmetic sequence. So I'll let you guys figure that out. Now I'm going to take a look at the homework while we're at it. So I'm going to pull up Delta Math, and I included a couple of review topics from exponential functions because we're going to have a final at some point, and I wanted to start reviewing now. So I'm going to include them slowly in the other examples. Also, there wasn't too much to do on Delta Math for this week's assignment. So our first example is on summation. I think I shouldn't have zoomed in so much. The problem asks us to evaluate, let me just open a blank page. So we're asked to evaluate the sum of the rule -2 minus n for examples 4 through 9. So 4, 5, 6, 7, 8, 9. So that would be my term number. And the rule, I'm going to call it a of n. So for 4, I'm just going to write 4 into the formula. So I'm going to do -2 minus 4. So that's going to be -6. So as I increase this to 5, that's going to become -7. So this appears to be a arithmetic sequence. So it's going to be -8, -9, -10, -11. And I'm going to add them all up. So, because it's a sum again. So just adding all of these up. That's -6 and -7 is -13, and -8 is -21, and -9 is -30, and -10 is -40, and -11 is -41. Now you'll notice in the front of this expression there was a 2, so we're going to multiply this by 2, but that's only because there's a 2 in the front of the expression, so we get -82. So all right, -82, submit. Oh, I made a mistake. Oh, let's see, what did I do? What did I forget? Oh, I misadded. Apparently I should have gotten 51 by adding, but I misadded. I would have then multiplied that by 2 and gotten -102, so that was an error on my part. Let's take a look at the second topic. So series to sigma notation. So we're going to be given an example like we were in the homework. And we're going to try and write this as a sigma notation. So the pattern is 3, then 12, and so on. So we're going from term 0 to the 57. Now the 57 appears to be term, see, so 12 is term 1, 21 is term 2, 30 is term 3, 39 is term 4, 48 is term 5, and 57 is term 6. So our expression is going to go n equals 0 to 6. The rule here appears to be add 8. Oh no, it can't be add 8 because, well, it's add 9. 3 plus 9 is 12, plus 9 is 21. So we're adding 9. So this is an arithmetic sequence. So it's going to be 9n, and our 0th term is 3. So I'm going to put in 6, I'm going to put in 0, and we're going to plug in 9. Is there a button for n? Guess I'm going to have to get that on my keyboard somehow. Alphabet, ABC, all right, n. And how do I go back? How do I get out here? Numbers, okay. Plus 3. And that's correct. So this example is arithmetic. Let's take a look for a geometric one. This one, the pattern appears to be plus 9, so that's arithmetic. This one is plus 7, so that's arithmetic again. And this one, plus 4, more arithmetic. This one is plus 3, so that's arithmetic. This one is plus 6. A lot of arithmetics here. Plus 10, plus 2. Are there any geometrics in here? Plus 10. It appears that they're all going to be arithmetic, at least here. But you'll have some examples to try that are geometric in your homework. Let's take a quick look at the Delta Math assignments for the review problems. They're basic exponential functions. So in case you forgot how to do them, the basic exponential formula is going to be y equals a times 1 plus or minus r to the x power, or where the starting value is going to be what we're given. So we're told the new car is purchased for $17,600, and the value of the car depreciates, which is a decreasing rate, so we're do minus 11.75%, which is 0.1175. And we want to know what the value of the car will be over 11 years. So I'm going to plug in 11 for the years, and I'm just going to use a calculator to determine this for us. So that would be 17,600 times 1 minus 0.1175 to the 11th power. And we get, it says to round in nearest penny, so it's 2 decimal points. So 445. So $4,450.15. Whoops. And let's take a look at the last problem type, because this one uses a logarithm, so we might need a reminder of how to do this. And this will be the last problem I do for this video, because I know it's running a little bit longer than I planned, but it's just because I'm doing Delta Math for a change in the video. We're asked to find, in this case, time, so it's a little different. So we're told the car is purchased for $22,300. So again, same formula. So our formula is y equals a 1 plus or minus r to the x power. We're told that our starting value is $22,300, and the value of a car is going to be depreciating. So again, we're going to do subtraction, but it doesn't always have to be. 0.075, which is 7.5%, and it says per year. It says to the nearest year, how long will it take for the value of the car to be $7,700? So we're not told the year in this case. We're actually told the dollars. So this is 7,700. So what we have to do is we have to isolate the expression with the exponent. So we're going to divide both sides by 22,300. And I'm going to use a calculator. So 7,700 divided by 22,300. I'm going to get 0.345291. So this is equal to 1 minus 0.075. Well, if we take away 7.5%, that should be remaining 92.5%, the x power. Now, on Delta Math, they're actually going to show you how to do a logarithm by taking a log of both sides. So you put a log on both sides. And then by the power rule, you can bring the x out in front. So you'll get log of 0.345291 equals x log 0.925. This is kind of like a version of the change of base formula. You can divide both sides by log of 0.925. That'll cancel out the log on this side. So we'll do that over here as well. Log 0.925. And we'll just see what our calculator gives us. So I'm going to pull up the calculator, put it on this side for a change. We'll do log of 0.345291 divided by log of, oh, I should have closed the parenthesis. Let me go back. Divided by log of 0.925. Close that, press enter, and it's 13.639. So let me open the problem back up. And it says to the nearest whole year, so that would be about 14 years. And it says we are correct. The only issue I could have had while doing my example in this case is that I had rounded this value because I wasn't sure how many decimal places I would need for it to be as accurate as possible. So the more decimal places you can take, the better. If you have any questions, make sure to ask in the private comments of the